Hi folks, this is DiffyQ Quiz 2. We're asked to find the general solution of this constant coefficient homogeneous ODE. So remember, the strategy here is we're thinking in the background y equals e to the mx. If we substitute that in, every time we take a derivative we kick out the coefficient m. And since all of these are constant coefficient, we'll be able to factor out the e to the mx and cancel it out. So we're going to be left with our so-called auxiliary equation, m squared minus m minus 12 is 0. Now we factor that the usual way, m minus 4 times m plus 3 is 0, and we get for m negative 3 and 4. Since we have different numbers here, we're going to have two linearly independent solutions, and from that we can construct our general solution, y equals c1 e to the minus 3x plus c2 e to the 4x. Since it's a second order ODE, all we need is two linearly independent solutions to form the fundamental set. And so that'll do it for number 1. Number 2, we're given an initial value problem. The first thing we have to do is find the general solution to this non-homogeneous ODE, and then we'll need to enforce the initial conditions. But remember, we only enforce the initial conditions until after we found the general solution. The first step in finding the general solution to the non-homogeneous DiffyQ is we look for the solution to the associated homogeneous DiffyQ. In other words, we take this and set it equal to 0. Well, surprise, surprise, that's the same DiffyQ that was in number 1. And so we already know the solution to this is c1 e to the minus 3x plus c2 e to the 4x. And this comprises what is known as the complementary solution. That's why the c is there. The solution to the non-homogeneous DiffyQ, remember then, is going to be the complementary solution plus what we call a particular solution. And the particular solution is the part of the solution that's going to get us this 7e to the minus 3x. So what we do is we make a guess. We'll make an ansatz here. What should this particular solution look like? Well, since it's a constant coefficient ODE, what kinds of functions, when you take derivatives and then linear combinations, are going to give you something like e to the minus 3x? Our original guess would be a constant times e to the minus 3x. The problem with that is that this is duplicated in the complementary solution. So if I substitute a e to the negative 3x into the differential equation, I'm going to get 0 on the right-hand side. I'm not going to get this. And so as we talked about in class, when we have duplication, we eliminate the duplication by giving us by slapping on a power of x. So we're going to guess the particular solution looks like that. This is linearly independent compared to this, so we shouldn't get 0 when we plug this in. So let's take our derivatives, yp prime. We use the product rule. A to the minus 3x minus 3ax e to the minus 3x. And then we take the derivative again. Minus 3a e to the minus 3x minus 3a e to the minus 3x plus 9ax e to the minus 3x. And so we get 9ax e to the minus 3x minus 6a e to the minus 3x. So that's yp double prime. And what we do is we substitute these into the non-homogeneous differential equation. Alright, so now we're going to determine the value of a by substituting it into this DiffyQ. So here's all the pieces parts we had before. So yp double prime, I'm going to have 9ax e to the minus 3x minus 6a e to the minus 3x minus y prime. Y prime is a e to the minus 3x minus 3ax e to the minus 3x minus 12y minus 12 times ax e to the minus 3x. And this is supposed to work out to be 7 e to the minus 3x. So as I go through and simplify, let's look at the x e to the negative 3x terms. I get 9 of them from here. I'm going to be getting positive 3 from here. That gives me a total of 12. And of course over here we subtract off the 12, so it cancels out. If I look at what's left over then, I have negative 6a e to the minus 3x minus 1a e to the minus 3x. So I get negative 7a e to the minus 3x is 7e to the minus 3x. This gives me that negative 7a is 7, which gives me a is negative 1. This tells me that my particular solution is negative 1x e to the minus 3x. That means that my general solution to the non-homogeneous ODE is c1 e to the minus 3x plus c2 e to the 4x minus x e to the minus 3x. To pin down the c1 and c2, now's the time when I impose the initial conditions. Y at 0 equals 1. I plug in x equals 0. I get c1 there plus c2 from that. I plug in x equals 0 there and get 0. So this has to be 1. Then I need to impose y prime at 0 is 10. Well, what's y prime at x? Minus 3c1 e to the minus 3x plus 4c2 e to the 4x. Then I use my chain rule here. Not chain rule, excuse me, product rule. Negative e to the minus 3x plus 3x e to the minus 3x. So what's y prime at 0? I get a negative 3c1 from here. I get a plus 4c2 from here. I get a minus 1 from there, and I get a 0 from there. And that all supposed to equal 10. So I get a system, two equations, two unknowns. c1 plus c2 is 1. Negative 3c2, excuse me, negative 3c1 plus 4c2 equals 11. You can do whatever you want. You can solve for c1, plug it back in. I've been working a lot with matrices recently, so I'm going to multiply the top row by 3. 3c1 plus 3c2 is 3, minus 3c1 plus 4c2 is 11. I'm going to add these equations then. And I'm going to get 7c2 is 14, gives me c2 is 2. So I know that c2 is 2. I can substitute back in. c1 plus c2 is 1. That gives me c1 is negative 1. So what does that mean? Well, this tells me the coefficient here of e to the minus 3x is negative 1. The coefficient of e to the 4x is 2. So I get my grand final solution. Y equals 2e to the 4x minus e to the minus 3x minus x e to the minus 3x. That'll do it for quiz 2.